This video has lots of great ideas around the World Cup and football that you can do in the maths classroom. Got some games to play, some puzzles, and then Lenny Williams has some wonderful ideas for construction using scrap material and also how to deconstruct Pythagoras' theorem using a piece of rope.
Hello, everybody. Welcome. This workshop is about playful learning, but we're going to focus on football, maths and challenges, puzzles, games, ideas that will be related to football. So we've got a lot prepared for you. I'm Tony. I think you know me already. I keep popping up in connection with AIMSEC, which I started about 20 years ago. Caroline?
My name's Caroline and I founded Bubbly Maths in 2005, and my purpose in life is that every child on earth love learning and specifically enjoy mathematics, and what better way to do that than work with teachers to share all of Tony's ideas and some of my own, and we've got the wonderful guest today, so that's why I do this. Lenny.
Hi there. Yeah, I'm Lenny Williams. Everybody knows me as Lenny. If I'm a friend, my real name's Glenn, and that's usually I'm only called Glenn when I'm in trouble. Officially I'm an engineer, but because I'm retired, I fall back on calling myself an entertainer now. And but I also love maths, and I think bringing fun and maths together that's my mission in life, to make maths fun, make it approachable, accessible, and to learn while you're laughing.
So today it's all about playful learning. And as Lenny said, if you can learn while you're laughing, I love that. That's playful learning, or even smiling, or just enjoying yourself, even if it's difficult. So today, and we're looking at, we've got the learning spiral. The concept of everything that Tony does with AIMSEC and all the work she does is working with the learning spiral. So you keep addressing the same idea again and again as you mature and your understanding grows, and expanding it as it grows, and making sure the foundation. And the beautiful thing about the spiral is if the foundation isn't in place, you can go down the spiral and then quickly climb up it again if you found that there's a gap in yours or your learners' understanding. And today we're looking at permutations, properties of 3D shapes, and this is all going to be as part of playful learning, give you lots of ideas. So we're going to work systematically, we're going to do averages and interpreting data to do with football in this case. So that's something you can use next week. And we've got transformations, and we've got the wonderful Lenny Williams who's going to literally demonstrate ways of sharing these ideas with your learners. We've got geometric constructions, and he'll be using geometric constructions, angles, and a lovely way of using the Pythagoras Theorem. So we're going to be counting teams and matches in the World Cup, properties of the icosahedron and a truncated icosahedron. I wonder what that's going to be. Interpreting data about goals, again, being systematic analysis, and exploring winning strategies. Tony's going to do the analysis on that one. And then we've got the lovely football game, which is something you can definitely do as a starter and have nice conversations about that. Tony.
Okay. Well, today it's all about playful learning, as we said. Finland ranks very highly in international competitions in student achievement. It really is one of the top ranking countries in the whole world. And for the Finnish teachers, play is very, very important. So much so that children don't start school until they're 7, whereas many children in England start when they're still 4, because they start in the year they have their 5th birthday. In Finland, they don't start till they're 7. The school hours are fewer than in many other countries. Homework's only for the oldest learners. There's no homework for younger learners. They're encouraged to play after school hours. And teachers and local authorities have greater autonomy than in many other high-performing countries. And so that is, this diagram here comes from Christina from the Department of Teacher Education at the University of Helsinki in Finland. So she has shown you on this diagram what she calls the blocks of playful learning. So she is talking about here flexibility. If you're playing a game or you're trying something and it doesn't work, try something else. Grit, that's, being determined to succeed because it's fun, and keeping going. Curiosity, interest, passion, sensitivity, creativity and imagination, a sense of beauty, all these things come into playful learning. Creating your own games maybe, but most important of all, not just hearing the teacher's talking, I'm listening, not just that, but actually doing something so that you discover the ideas, how they connect to each other. You sort of grope for understanding, you find out, you manage to solve some puzzles, you learn from that, and then the teacher helps you to sort out those ideas so that you have got them all straight, you've got the right mathematical language, and you've made progress in your learning. But not just by listening to the teacher, by actual playing with the maths. My husband's a mathematician, and he says that when he's trying to solve a problem that nobody's ever solved before, which he can't do himself, but he thinks it's likely that something's true or important, he plays with the ideas, plays with them, and gradually makes sense of the ideas. And that's what we want our learners in the classroom to do. So Caroline is going to tell us something about why does play matter?
So my instinct is that play matters, but fortunately there's research to back it up, and research shows that there is a clear relationship between academic achievement and the experiences of play and development. Now, this includes self-regulatory skills in terms of things like learning to handle failure, learn like how you handle losing. It's how you handle the negatives that ensure that if you learn to handle them well, that ensures success, because you've got perseverance and determination, and you learn that through play. So if you don't understand something, you're stuck, then the best way is to play, as Tony's husband, the lovely Alan, does. Just play and create your own examples and have a go in different ways, and play with other people. So it motivates you to concentrate better. This is where all the research is going. It teaches to persevere. If you don't succeed, all that lovely perseverance and determination. You build up through play. You literally build the skills you need in life. And learners can develop by playing with others, great communication, teamworking, and even being sensitive to others. So reading what others are doing and working with others in such a way that leads on from teamwork. And so you've got really healthy social interaction. And then we're all very aware, 21st century education, the children that in our schools now are going to need to adapt to change like we've never seen before, to taking new roles, learning new things, adapt on a the spin of a coin, and to be constantly understanding new ideas and technologies, not just at work but also at home. And creative problem solving is one of the key requests that people in industry, that businesses, large businesses, small businesses, they want creative problem solvers, people with resilience and flexibility and able to respond well whenever there's changes. That's critical to jobs in this century.
Sometimes the problem is about making our work as whatever we do, whatever our work is, more efficient. And the way it's it's optimization. It's often analyzed. That's the problem. It's often analyzed in a mathematical way. Anyway, let's move on. Caroline, you're going to introduce something to do with the World Cup that's happening now.
Yes, right now. So we're just going back. Tony's pulled up all not the league tables, the groups, all the different groups. So they're all listed there. And we want to know where the maths is. We were looking at that at the beginning. Where's the maths in that picture? It was direction of ball, everyone making calculations about what they need to do, where they need to be, and how to score that goal. And then if you look on the right, you've got all the different groups with all the different countries that are in these rounds. So the questions are, 2 teams from each group qualify for the knockout competition. So how many games are there in the group rounds? How many teams play in the knockouts? And how many games are played in the whole tournament?
And there's an organization behind it. So I think this is rather a good set of questions for a lesson. If the learners actually know the answers, somebody may know how many games and so on, or how many teams go on to the knockouts. But how does that come about? Why does that number have to be the answer? So Talu has said 6 games in each group, and there are 8 groups. So there are 6 games in each group. Talu is right. And there are 8 groups. So that's 6 times 8 is 48 games. And in our what we teach in maths and what we want our learners to be able to do, we quite often, that's permutations in action. We have to, when we're counting the number of possibilities and working out probability problems, that's often the sort of thinking that we have to do. So that's the number of games in the groups round, and then the 2 teams from each group qualify for the knockouts, and there are 8 groups. So that's 16 teams, not 24, but 16 that go on to the next round. And then how many knockout games? Now, I love this way of thinking, because you can now ask your class to answer that question. And here's one method. There are 16 teams and 15 must be knocked out. Now, only 1 team is knocked out each match. Okay. So in the round that's starting now with the 16 teams, 15 must be knocked out. At least they won't be the winners, to determine the winner. And there's also a game to determine 3rd place. So there must be, from method 1, we can see there are 15 games between each, as you go down, it's going, and then the last one, extra one, as it were, to determine the 3rd place. So this is how it works out. In the round of 16 teams, there are 8 games between those 16 teams. 8 teams drop out, and there are 8 teams left. And in the round of 8, there are 4 matches, 4 games, and 4 teams drop out. And then we come to the round of 4, when there are 2 matches, and then we're left with 2 teams who play, the teams that play for in the final, and the teams that come second in that round of 4, they play for 3rd place. So there are 16 games altogether. And so how many games altogether? Well, it's 48 that we counted in the preliminary rounds, and there are 16 more games to look forward to.
We could call it a truncated icosahedron, but what does it look like? Whoops, it looks like something that's inflated. We could call it an inflated truncated icosahedron. Now, it's not the ball they use in the World Cup, but it is your classic football. It's the same format. You've got a certain amount of faces, a certain amount of edges, and a certain amount of vertices. So the first question is, how many? How many faces, how many edges, and how many vertices? What you can see on the screen might help you there. You can work it out quite systematically. And then we do have an extra question. So if you finish that, there's a question at the bottom.
They can just count the faces, can't they? Then they've got some working out to do.
Yes, you can just count the faces. But if you do it systematically, think about whether you're counting the hexagon or the pentagon. That helps. So we've got 32 faces from Talu.
Well done, Talu. You're right, of course.
12 pentagons and 20.
Yes. How many edges? How many vertices?
You can count them, but it kind of messes with your head. If you can calculate them, it's much easier. Hello, Pam. No, you cannot use Euler's relations straight away.
She's joking.
Yes, I know. Ha ha ha. And of course, this isn't about whether or not you know this. It's about helping your learners discover it.
And yes, and doing it today so that you can get a feel for what the learners have to do to find an answer. Okay, well, let's look at the answers. Okay, so we can count, and so if we count the yellow hexagons, there are 20, and there are 12 pentagons, making 32 altogether. Now we can work out the number of edges. Each of the hexagons has got 6 edges, so that makes 20 times 6, 120. And each of the pentagons has got 5 edges, so that's 12 times 5, which is 60, 180 altogether. Now, each edge, of course, and when we make up the buckyball, that's what we call it, they belong in 2 faces, and so we divide by 2, so we get 90. And then for the vertices, we get the answer 60, as Pam has just given us. Again, this is now counting the vertices. Each hexagon's got 6 vertices, and each pentagon has got 5. So altogether, there are also 180 vertices altogether. But, well, counting them face by face, as it were, before you start joining up the faces. But you join 3 faces at each vertex. So we divide by 3 to get a total of 60. And then this is what Pam mentioned. If you
can I just point out the calculation that Pam has done? She's used observation to notice that every pentagon has 1 unique vertex. So she simply added up all the vertices of all the pentagons, and that way you also get to 60. You've got 12 times 5 unique vertices, and there are no others.
Right, that's lovely. I like that, because each pentagon is surrounded by hexagons, but they don't add any new edges or vertices. That's lovely.
New vertices, yeah.
So when we come to this thing at the bottom there, the number of faces plus the number of vertices minus the number of edges, this is something your learners could investigate with simple shapes like cubes and pyramids and other shapes. And it turns out that they'll all have the answer. When you work that out for different solids, will always have the answer too, and that's called Euler's formula or Euler's relation. Now, we've been talking about the icosahedron. Caroline.
Yes, the icosahedron is, this is one of my favorite things. You remember we called it originally, we called it a truncated icosahedron.
Well, that's the buckyball. Is this?
That's the buckyball. So if we look at the we're looking at how to produce a buckyball from, why do we call it a truncated icosahedron? See if you can identify, we've got the hexagons and pentagons there. How did we get the hexagons and pentagons on the Buckminster fullerene, the buckyball, the carbon-60 molecule? It's all of those. It's a structure of all of those things. The football, the traditional football. How have we truncated it? How can you see it? Can you visualize it? So the question is, how is a buckyball produced? By cutting off pieces of an icosahedron, which is called truncating. Can you visualize it? Can you describe it in the, again, put yourself in the position of your learners?
I love the question. What do you see in this picture? That's a lovely way to start a lesson. If we were to give this picture of these two solids side by side and say, what do you see here? There's so much your learners can say about it. Why have I chosen to put in that picture of the icosahedron where each face is split up into smaller faces? Okay, and I had a good reason for doing that. You'll see that in a minute. But
Melanie has said chop off the corners.
Well done, Melanie. Yes. And Melanie can see what's happening. Melanie and Caroline made that lovely buckyball together. Show us it again, Caroline. There you go.
And then we had an extension question, was how many pieces of tape do you need? And that is a very relevant question because your learners will be asking that question, believe you me.
Yes, it actually helps to get the tape ready before you start. And of course, the reason it's not the number of edges is because some of the edges in the nets there are joined already. Now, actually, what you can do with your class, and I will give you the PDF with it on, Caroline has used this PDF, which I'll share with you, which is that picture you see there, to make that. It's a two-person job, isn't it, Caroline?
Definitely. Even just preparing the strips of tape. And just so that you know, what we did is, because we don't want big, thick strips, we just got a long strip of tape and cut it into teeny, just slivers of tape. And that made life a lot easier. But we did want to know how many we needed to prepare, because one of us was cutting the tape, the other one was putting it together with helping each other as well. So it was
and you put some of the sticky tape inside, and then when you got it nearly finished, you had to put the last few on the outside. Yes.
Yeah. And as Melanie says, you need, in the real world, you need extra tape pieces for mistakes, which we did. Definitely need more than
right. So moving on, now Melanie's answers is that you chop off the corners. Now you should be able to see why I chose that particular image of an icosahedron to show you what you do. So you chop off a pentagonal pyramid, a pyramid with a pentagonal base, from each of the vertices, the 12 vertices of the icosahedron, and that gives you 12 faces for our buckyball. And you can see that each red pentagonal face is surrounded by 20 golden colored hexagons. And while Caroline mentioned that this buckyball is not only the shape that's commonly used for footballs, but it's also a structure that is often used for making what we call geodesic domes. And there are a lot of buildings which are either entirely a geodesic dome or are, you know, have the geodesic dome and the roof part of it. And it's not just this particular set of different shapes, but this is one that's often used. And Buckminster Fuller, who produced all these ideas and related it to the carbon atom, was a man who was designing these geodesic domes. So that's interesting, I think. So Lenny, over to you.
Hello there. So we're going to have some fun, and we're going to observe some mathematical things as we go along. So the emphasis being on fun, because I'm an entertainer before I'm a mathematician. So what you're going to need for this is 2 pencils. You can get away with 2 pens, but you can't rub out a pen as easy as you can with a pencil. Straight edge, something to draw your circle on, and a compass. Now, if you don't have an actual compass, I was actually trying to explain how circles. There are things you can do that you find around the house. You can get a short piece of string, maybe say that long, create a loop, just tie 2 ends. You can use that as a compass. But I've been converted. I've used a credit card, punched 2 holes with a pencil in either end. I've used paperclip, anything that holds the 2 pencils the same distance apart. I've even used my watch, because watches have holes that don't move right apart there, and I created lovely shapes from that. I'll show you later, but I'm going to show you quickly how to make a plastic compass. And what I'll do, just kind of strip. Just found this line around the house. You do this yourself. There you are. So that's just a strip of plastic. And
Lenny, I absolutely love that, because basically at AIMSEC, we try and find as many ways that we can make learning resources from junk.
Yeah, that's effectively what it is. You can almost, you've almost always got something in your pocket. It might be a credit card, a piece of string. I don't know how many people walk around with pieces of string, and yeah, or anything. Sometimes you get rulers, and okay, as usual, hidden it. So basically, what I do, I get something sharp, might be something like this. Get a pen, and I'm just going to punch a hole in one side, like this. I'm doing this with a foam backing and a hole in the other side. And I can put other holes just for fun to create other shapes. So that effectively is going to be my compass, 2 holes. Okay, so how do I use that? There's lots of different ways. So make sure your pencils are quite sharp. And also, it's also a good idea to make sure your holes are large enough for your pencils to go through. Sometimes I get a nail file and nail those down the back. So I'm going to put my plastic compass in the center of the paper, and this is going to be the center. So I'm going to hold this in place, and I'm going to put my pencil in the other hole, and I start to draw. Don't press too hard because it makes it difficult, but try to be fairly smooth. If you can't go all the way around, which you often can't, just hold the pencils in the same center and carry on around. So there you go, you've got a lovely circle. You can't see that, I'll just lift that. Can you see that? I'm not sure if that's clear. So that's a circle. Okay, so that's quite fun. So we can create a circle. Why do we know it's a circle? Because the edge, the circumference is the same distance from the center all the way around. That is the definition of a circle. but we can have even more fun. So what I'll do here is I'll put one of the holes on the edge of the circle. Make sure it's on the edge. There you are. So it's sitting on the edge, and I'm going to use my other pencil and I'm going to draw an arc, which means part of a circle. Okay, and I'm just drawing it from edge to edge, like that. So that's an arc. Great. Now, the arc intersects the circle in two places, there and there. So I'm going to put my pencil on this intersecting edge. I could use that. I'm going to go for that one. And I'm going to draw another arc from that position. I don't know if anyone's following this with me, but I'll continue on. So make sure it's on the edge exactly where the two lines intersect, and I draw another arch.
The teachers could do it if they had a paper clip.
Yeah.
I cut off a piece of the edge of one of those plastic pouches that you put paper in. I cut off a piece of that, and I'm using two of the holes on that.
Yeah, that's a bit of a birthday card with two holes. And I put another hole in the center just to create more shape. So using my same plastic compass, giving it a grand name, I'm going to go for the last intersection point there. Where the last arc intersects the circle, draw another arc. Okay, so how many arcs do I have at the moment? Anyone want to answer? I've got 3. How many arcs do you think I can fit into that circle if I continue? How many arcs in all? So while you're thinking, I'll carry on. It'll probably become clear. So I'm going to go to my last intersection, so my third intersection, where the two lines meet, and draw another arc. Now this arc is the same circumference as the original circle. I can actually, if I'm clever, not take my pencils off the paper. As long as I'm on the edge, I can continue like this. I'm going to show off a bit now.
Oh, that's difficult, Lenny. I'm having to do it with my left hand now. That's tough.
You are allowed to change hands.
Well, I did it with my left hand.
So there we are. That's the 6-sided petal flower, 6-petaled flower. We're calling it the flower of life, because it's sort of nature. Nature loves circles. Nature loves spheres before it loves circles in 3D, and then circles, spheres on flat surfaces create circles. These arcs are all the same circumference, which happens to be the same circumference as the circle, which means that the distance from this point to that point and that point to that point are all the same. So you could call that a regular flower or a regular shape. I can do some nice things with this. Okay, if I've got a straight edge, and I'll give these points names, A, B, C, D, E, and F, around in a circle. I could have given them numbers, but I try to avoid numbers, as I said. I'm a mathematician that doesn't like numbers. So I'm going to join point A, tip of the petal A, to tip of petal C. So I'm going to jump. I'm going to draw from A to C, C to E, and then back to A. 3 lines. Nice thing about this, it actually doesn't matter too much. If you're not entirely accurate, it still looks great, whatever happens. So there we are. So now we know that the petals are evenly spaced, meaning every other shape is evenly spaced. So we know that these lines that are crossing are the same length. And what do we call a triangle that has equal length sides? Call that an equilateral, meaning equal-sided. So that's an equilateral. And what are the angles here? All the angles in a triangle add up to 180 degrees. 60. There are different ways to prove that. If I continued my shape and kept adding the equilateral triangles the same size, or cut the shape out, I'd end up with 6 in a circle, a hexagon effectively of equilateral triangles. And then you could say 360 degrees divided by 6 triangles equals 60 degrees. So that's one way to do it. You can get the children to cut that shape out 6 times and place them together. They'll see it's 6, and then you can say, well, a full circle is 360 degrees divided by 6 gives you 60. Or you can remember the rule that 180 degrees, all angles add up to 180 degrees. We have 3, so 180 divided by 3 equals 60 degrees. Create another equilateral triangle upside down effectively, and see what shape we get. Might call that shape a star. So we've got 2 overlapping equilateral triangles. How many triangles can you see in that shape?
You just said similar, but the ones I've just drawn are congruent, but now we've got, oh, okay, how many are there?
Yeah.
I can see small triangles, but I can see a star.
I can
see a star, which is beautiful.
and I can see a hexagon. So what can you see? So put the ahead of your learners on and describe what you can see. What?
Well, I'm going to create a hexagon. Yeah. Okay. So before I draw the hexagon, I don't want to get ahead of myself.
You have drawn a hexagon, Lenny. You've drawn a hexagon. It's there.
Oh, I have.
In the middle.
Oh, brilliant. Okay, right.
But Lenny, yes. What you, as a teacher,
yes,
you know, the learners could do this diagram and then stop. Then tell them, ask the question, what do you see?
What shapes do you see? Yeah.
What shapes do you see? Why did you give that answer? Where is it? Show us. Yeah.
Yes, lovely. You might see other shapes. You might see a cat. Can you see a cat there? Can you see the cat?
Nice imagination.
Shall I show you the cat?
I can. Oh my goodness! I think I can see 2 ears.
Okay, I might not do it on this one.
Lenny, by the way, is an artist as well as his many other talents.
Okay, all right, here we go.
Wonderful art.
Here's my cat. I don't know how much of this you can see.
We can see it.
There we are. There we are. Or we might call it a rabbit.
There it is. 2 ears and then the face.
It takes a little bit more imagination, obviously. So there we go. We've got a lovely cat. Bit of a tangram there, I think we got. What other shapes can we see? So we can see smaller triangles, I think you said, Tony. And
smaller and bigger triangles. Yeah.
And guess what? They happen to be equilateral triangles as well.
Lenny, you've also got parallel lines in that diagram.
You have got parallel lines. Oh, that's lovely. Does anyone know what this angle is here? And also happens to be that angle there. So in blue, I've drawn some new angles. Does anyone know what those angles are? And while you're thinking of that, I'm going to finish this off, and I'm going to draw the big hexagon around the outside.
So, Lenny, this is what we want the children to answer, 120 degrees, and then, which Talos has written on the chat, but also we want the children to explain how they got that. Yeah. And they got that from taking 180 minus 60. So the 2 line angles are sitting side by side. Yeah. That is the 60-degree angle and this blue one. And so, so the blue one must be 120 to make up 180. Brilliant. And Lenny, you had in your hand a minute ago a lovely coloured version of that pattern. And what that shows how you can invite your learners to be creative. Then he's going to show us, because your time's more or less up, Lenny. Then he's going to show us the coloured pattern you had a minute ago.
So that was one that I did. I sent you a PDF version. That's one with all the angles drawn. So I put yellow for 60, purple for 120, and you've got little angles in the corner here, and they happen to be 30 degrees. So
and then you had some coloured in as well. Where are the coloured in ones?
Colouring the petals. You see, what I'm suggesting is that we want the children, especially if we're talking about younger children, to create patterns for themselves. So based on based on this principle that you're showing us,
Yeah.
there's so many different patterns that you can, lovely designs that you can make. And
That's similar.
that one with the orange rim and oh, it's just lovely. Thank you, Lenny. I've got a message for you to decode on the screen. This activity stands on its own. You can encourage the learners to make up their own codes. This is a substitution code. Every time you see the number 5, it gives you A. And every time you see the number 4, it gives you T. And for all the other 26 letters of the alphabet, you can have different numbers. So substitution code. You write the messages that you've got here. What are the words that you get in that block? 199. Ah, so Owen has said foot is the top 1994 or 1994. Ball is the middle one, and game is the one below. So that is introducing us to another activity, but that's an activity that stands on its own. So decoding the message, you get foot plus ball equals game. Notice that the arithmetic works here, doesn't it? And now find all solutions to the foot plus ball plus game puzzle here to these 3 puzzles. Now, this is a simple introduction to foot plus ball equals game. Actually, when you work on this puzzle, starting with the raw foot plus ball equals game, there are 224 solutions. So an easy way into it is to do some simple puzzles where you're given some of the numbers, but to replace the letters, but not all of them. Okay, so in the first one, you're given 2004, so that's quite hard. The bottom one is the easiest one because you've only got 3 letters to find. You're given 9 numbers.
As Tony said, if you do foot plus ball equals game, you're finding all the numbers, it's a bit challenging. So I'm going to start with 2004. We're not using the original code. We're figuring out a new code now, so each letter will have a different number.
Yes, they're different sorts of activity. The decoding is a different sort of activity, and you might want to use that. This one is a cryptorhythm, they're called, these puzzles, where you're given letters and you have to find the right numbers to replace the letters. And you're not allowed, you see, in ball and game, A has got to be replaced by the same number, but you're not allowed to use the same number if the letters are different.
Right, so and that gives you a nice big clue. And you've got the L's have got to be the same number. So 4 plus something is going to give you E, and 0 plus the same thing is going to give you M. 0 plus the same thing is going to give you M. And you use that to work out all the different possibilities, and you can do it by trial and error, and then you can start working out, wait a minute, that's not possible. So and then you can eliminate things that aren't possible, so you're not actually attempting every single number. And as Tony says, once one solution has been found, you then want to find others, so change some of the digits. Now, if you notice on obviously L and L are the same.
In this example, for 7 and 1, you might have found, some of you might have found one of these answers, some of you might have found the other, but there are actually 2. So that's nice. In the class, you can say to the children, who can find an answer to this? And the ones who have quickly found one of the answers can then search for a different one. Or you may find that people in the class come up with one answer, other people come up with the other.
If you decide that F is 2, E cannot be 2. Each letter is unique.
And there are some solutions.
Do know then that L,
Hmm.
you know, you're going to have a double number in ball, and you've got the same hundreds column number in digit in for A, because of A being the same.
Now you'll see for the second of these puzzles, there are actually 4 very similar solutions, all starting with 1007 and all having 2000, some hundreds and tens and 8 units. There are all of those, 4 of them. Interesting. Then he says it's a bit like mathematical Sudoku. Yes, well, Sudoku is mathematical in a way. It's lots of reasoning. Yes, I agree with you, Lenny. So can you find a solution to the last one? It's very easy. You've got L has to be 3, so you've only got to do T and E, and they've got to be 2 numbers that don't already appear for one of the other letters. L is obviously 3 because there's 2 L's in ball, so you've got to find T and E. A child and improvement. I've now shown you the solution. It's 1994 plus 6533 is 8527, and there isn't another solution. Here's some reasoning, a proof for your oldest learners. The letter O can only take values 0 and 9. You might ask why. You know, surely the letter O can be any one of the 10 digits, but it actually can't. And let's see why that is. Either one is carried over from the tens column to the hundreds column, or it isn't. So there's 2 cases. So let's look at the hundreds column. If one's carried over, we know that then 1 plus whatever value O takes plus A has to, which gives you, must add up to A, so it must add up to 10 plus A. So the number O must stand for 9, and that's the first case. Right, you're looking at the hundreds column now. This is a good one for your place value, Caroline. You were asking about place value examples.
Yes. Yeah.
So now we're looking at that, but the reasoning is, you know, you've got to think very carefully. So it's you know, there's only 2 possibilities, or there's no carryover from the tens column to the hundreds column. If there's no carryover, 0 plus A equals A, that's fine. Whatever O stands for plus A is A, and so the letter O must stand for 0. So that shows you that that letter O has to be 9 or 0. A minute to think about that. And I think you could engage your class in a discussion of why those are the only 2 possibilities. If you want to, slide 33, which we're not going to be showing this afternoon, will tell you more, and there are full explanations and solutions on Aiming High.
Follow the link to the Aiming High activity in the description to find the solution.
Here is a lesson suggestion for a systematic method for finding solutions. Right? Now, we don't really need to understand, the learners to understand why O can only take the values 0 and 9. We can tell them, let's assume this to start with, or let's just assume that this is the case. So let's see which, so what solutions can we find? So this is going to be, we're going to have to take each of the cases in turn. First of all, the letter O is 0, and then the letter O is 9. So this is how your lesson might proceed. You could first ask the learners what they can deduce about L and M from the tens column, okay, when the letter O stands for 9. So you've got 9 plus L equals M. there. And I'm not going to dwell on this because I think you can take some time to think about it afterwards. But the answer is actually m is L minus 1, or 1 plus m is equal to L. That's where you have got O is 9. So in this case, there cannot be any carryover from the units column. So what does this tell you about T plus L? So you want the learners to think about that, and those are the answers there. So they now have got something that's going to tell them about a little bit more information, not just about the letter O, but about the letter M, the letter L, and the letter T. So they now have got only a few, well, they've reduced the number of possibilities for the TL pairs. And you know that once you've explored up to now, you'll everybody through discussion in the classroom should be convinced that T and L have to add up to something less than 8. They can't add up to 9 or 10 in this case. And so now you can share the work of finding the solutions in these cases. So as a teacher, you can give different values of TL pairs to different learners. So you can, everybody does a bit, and then everybody will be able to find their own solution and share, or you make a poster that you put it on the wall. I love this sort of activity because it's something that the learners can, lots of learners can contribute to. Once they find a solution, that should go up on the poster on the wall, you know, or they should get a gold star or something because they found a solution that nobody else has found. They'll be the first one to find a particular solution. And because there's so many solutions, there's lots of opportunities. And this is building into the head, into the brain, powers of reasoning, mathematical thinking and logical reasoning. And once they're finding these solutions, you can discuss the best way to record the solutions on a chart in a systematic way. So there you have an outline of a lesson.
We're going back to football and we're looking at averages. So we've got 2 questions here. Looking at them carefully, the first question is, and they're numbered 1, 2, 3, 4, 5, 6. Which chart gives the same information as the tally chart? So the tally chart's chart 6.
This is about data representation, isn't it? And there's so much in football about data, all sorts of results and statistics. So it's a very rich area for finding data that the learners might be interested in, especially if it's relating to their own team or local team or the team they support.
Melanie and Talu both say chart 4, which is the pictogram.
Yes, that's right. What about the pie chart? Which is the same as the pie chart?
Melanie says it's 5, the frequency diagram.
Well done, well done, well done. Okay. Can you see the large number there? So that is the mode, 1 goal there. So that seems to link them. And we're told that there's several representations for the same. So we've got Alpha United and Beta Rovers. Let's explore this data a little bit more. So I've taken those 2 sets of the tally chart and the pictogram, and I want you to calculate, this is an example you could give to your learners, you can do it quickly, the mean, median and mode there. Okay.
Right, so we need to work out the mean, median, mode. Okay, I'm on it.
So in order to do that, you need to do that if you want to find whether it's Alpha United or Beta Rovers, because the other information is about the mean, median and mode. We've got no goals 3 times. We've got 1 goal 3 times. So it's one, we're counting goals now. It's 1 times 3 plus 2 times 2 plus 3 times 5 plus 4 times 2. And that gives us 30 goals altogether. So to work out the mean, we divide that by 15, because there are 15 matches, and we get the answer. The mean is 2. And then if you write the list of goals scored, in an increasing sequence like I have done, as you see it on the screen, you can see that the median is 2. So what does that tell you? So here is the information about the 2 teams. Their point is they weren't named, as Pam spotted, in all 6. They were only named in 2 of those pieces of data given. So is this one Alpha United or is it Beta Rovers? The mean number of goals scored by Alpha United is equal to the median. Well, certainly that's true. 2 equals 2 here. And the mode is 1 more than the mean. Yes, that looks as if this is Alpha United, and there's a summary of all the results. So we now know that those 3 pieces of data are for Alpha United, and Caroline will now talk you through these 2 pieces of data, which we know must be the other team. And now, in order to check everything, you want to work out the mean, the median, and the mode again.
And yeah, so simply do what you did with the other. Melanie's asking, do we want the mode, median, and mean and median per match? It's combining all the matches. So we want the mean, mode, and median of all the matches combined. So how many?
So it's how many? So it's an average, Melanie, of 2 per match in the last one here. Because the mean was 2, it means on average there was 2 goals scored in each match. Now we know that in some matches there were no goals, and in other matches there were 4 goals. So anyway, that's what it is. So there's the answers. Okay. Now this is different from the last one, because this one it's very, very, very similar. The mean's 2 again, although it's calculated in it. Now we would expect it to be the same because we're relating to the same matches, but now the mode is 1, and it was 3. It was in the previous one here that the mode was 3. Now in this one the mode is 1, and there are the list of the goals scored, and the median is 2 again. So we expect the mean and the median. Melanie's remark was really helpful. We expect them to be the same. It's only the mode that changes here because they relate to the same matches, as Caroline said. So that's for Beta Rovers, and there is the summary of all the results. Okay, so that's another football related activity. Now this isn't particularly football related, but we thought you might like to try a new game. And this is the game. It's very simple. It's just played on a grid of 16 4x4 grid, 16 squares. There's only the pieces you see there, 2 L-shaped pieces and 2 black pieces, and you can't have the pieces overlapping, and the game proceeds. These are the rules. You can move the pieces. So when it's your turn, supposing you're red, you can move the red piece, and you don't have to, but if you choose, you can move 1, but not both. The black pieces, either player can move. The L shapes, one belongs to one player and one belongs to the other, and you've got to try and block in the other player. Okay, so Melanie and Caroline are now going to have a game.
So we have Melanie's going to start with red. So you can move the L shape anywhere and you can completely change. So at the moment she's just
Translated it to
thank
the
you.
right.
To the right, the one place, and then she's moved the dot, that dot, she's translated that down 4 places. So I'm going to just to demonstrate that you can do it, I'm going to take the green and going to place it there. Now I want to stop Melanie being able to move hers. And I can see a move that she can still do.
I'm going to turn mine around like that. And I want to stop you going up there. But if I move that one, you can go there. So
It's a bit of a game that looks, it's one of those, looks very, very simple, but now I think that there. Now Melanie can't put anything there. She could put something here, and I can't put my black dot under hers. So this is not going to stop Melanie at all.
Melanie's got a lot of scope now, Caroline.
She does have a lot of scope.
You don't have to move the black piece, Melanie, but you can.
Yeah. We've played this a few times now. Melanie won this morning.
I cheated.
We did actually look. We were attempting to look at the solutions. I'm going to.
Oh. Oh.
Yes, I'm going to leave that there. Could go on forever doing that.
I seem to have seen that actual sort of position, but rotated if you get a few moves back.
Yeah, and the other thing we were talking about, Tony, wasn't it, was using the language. So I'm going to rotate this L about the center, about the vertical center, and that's I'm actually no longer even thinking about the strategy. I'm thinking now about the language that I'm using.
You think about the strategy, Caroline. We want this game to finish. Come on, Melanie.
How long have we got?
I'm on your side, Melanie. You've got to beat Caroline.
Thank you, Tony.
All I can do is either that or that.
Don't do that.
Or that.
Yes. Better.
That's not where I was, is it?
You were there. No, you were there.
Oh, I was
think.
there.
Yes, I think
Oh,
so.
you've got to remember where you were as well.
I
Yeah,
will
that's a
go
good
there.
point.
And then I want to, so you can't go there. And you could flip over. So no, I haven't got you yet. Oh no. Good. You've got loads of choices now.
Yes, I've got loads of choices.
It actually can be quite short, and I think what I'm going to show you is some of the strategies now. And if you're really determined to win and you think of some of the strategies, then I think it doesn't have to be a long game. Although I'm not absolutely sure, because if your opponent is also an expert,
that's what we were finding, that unless you make a mistake, it can go on forever, we think.
Well, I don't think it can go on forever.
Go on, show us the strategies.
First of all, I'm not going to, this is not about strategies particularly, but it's really about, you know, the maths in this game. What you can do is you can describe the, you know, where you put your L by saying whether it's going to be translated, reflected, or rotated. So it's a really good example for exercising those ideas of transformations which we teach in school. So what I want you to look at now is these two diagrams. So, and say, if you see that starting position is number 1, so just moving the board or reflecting the board, you can get all the other positions that you see there. So I want you to describe the transformation of arrangement 1 that gives the other arrangements numbered 2, 3, 4, etc. up to 7. So how would you describe the change from 1 to 2, for example, and the change from 1 to 3, or from 1 to 5? Now, what we're pursuing here is a better understanding of the layouts so that we can work out some strategies.
Starting with arrangement 1, arrangement 2, I can't do without moving everything around because it's not a rotation, it's a reflection. It's a reflection about the central axis. Number 3, if maybe you could, in the chat, you could actually choose a number and say what you think it is. And at 4, I've actually done that. 4 is a rotation through 180 degrees. 3 is, oh, we've got some comments. I'm not sure if I've got comments going on there. I'm just getting my head around what 3 is. 3 is, it's rotated, not rotated, it's reflected on the bottom. So it's reflected along this line here, along the base line. And is it anything else? It could be a combination as well of a rotation and a reflection along a more vertical line, perhaps.
So what we have got is rotations as well. In Caroline showed us the rotations. She couldn't actually physically do the reflections, but you can see that you've got arrangement 4 is actually 2 reflections.
Or rotation, 180 degree rotation. That one I was able to achieve.
That gives you the same. And yes, so we've got, well, we're actually going to regard all of those arrangements for the purposes of this game as being the same. So they, in effect, they are the same, but they're just reflections and rotations. The same in the way they're equivalent, in the same way as 5/10 is equivalent to a half, or 3/4 is equivalent to 15/20, and so on. So they're equivalent. And so here is a lesson that you could run with your learners to help them to investigate this game and to find the strategies for winning. So they learn the game. You could play the game with the class in 2 teams, and then there's puzzle 1. We'll come on to that. Pamela asked about the black pieces. The rule there is that either player can move either one or the other black piece, choosing the one they want to move any time. I think you saw Melanie and Caroline doing that. So here is puzzle 1.
And one thing that Melanie noticed is that you, in case you ever thought of that, you cannot move the black piece first. It has to be after you've moved your L shape, then you can move your black piece. Otherwise, whatever blocking your opponent has done is completely redundant. So it's move your L shape, then one of the black pieces if you want to. You don't have to move a black piece.
So the first exercise for the learners is to find all possible positions of the red L on the board. That's the starting position for the red L, but it could be in lots of other places on the board. Okay, so here are some of them. Now, of course, you can have that position rotated or reflected, but they would be equivalent. So now, step 2 of your lesson is the whole class solves puzzle 1 and shares the results. So if there are any more, if there are other positions, and I think Caroline found some I hadn't put here, if there are other positions of the L that are not reflections of rotations of these positions, then somebody in the class, you hope, will find them. Okay, now then, puzzle 2. The next task for the class is to share the work. So different groups in the class each tackle one of the positions for red. There's 6 different ones there, however many there are. You get a group of learners to take that same position and find all the possible positions. This is puzzle 2, where they can put the blue counter. So what we're looking is winning positions, and we're looking for all the possible positions. And there are some of the red-blue positions on the board. Now, you might be able to find others. And when you get the class to do this, you don't show them, you let them come up on the board. If they can find another one, they can put it amongst the collection that's found, that the class has found. And then you should have all the possible positions of red and blue L's, but of course not including ones which are reflections and rotations, which are equivalent.
Something else you can do, Tony, just occurred to me, is you can play the game. We can do all these little challenges, and you can also add to this. Let's say in this position, where would you have to, if it was green's turn next, for example, where would you have to put the black dots in order to prevent green from going? So where would the black dots have to be? So instead of revealing the winning positions, you can get the learners themselves to discover the winning positions without.
That's challenge 4 in this lesson.
Oh, is it already? Sorry, I beg your pardon. I missed that one.
Well, you get the groups to take the pictures that you see with the red and blue on the board and decide where they would put the blacks to block the other L in. And then they discuss winning strategies. Now, also, computers are programmed to beat the best human players at all sorts of games, including this one. And what they do is they take into account all the possibilities, which is hard for people to do and remember them all. This is a challenge. This is artificial intelligence in action. So the class could talk about artificial intelligence. And then if the class studies the winning positions, then they all now are really knowledgeable about the game. And then you could run a league competition to find the champion. All right, so everybody could play another player, and then all the winners could go on to the next round, and then all the winners to the next round, rather like the World Cup. So here are some possible final positions where blue has won. Now, if you try to put now where red could go, blue has won. So can red go anywhere? And the answer is, in these positions, red is stuck. And in most of them, red is stuck in a corner. So immediately this tells you that if you try not to put your L in a corner, if you can help it, and your attacking position is to push your other opponent into a corner. Okay, so that's a good strategy. And Caroline is showing us the pictures on the left show you how blue is blocking in red, with red in a corner in the same way, but by moving the black position, but that counters, you don't leave any space for red to move into. And so now,
And this has 3 winning positions. This or this would all have the same effect, would all block red from moving.
now actually the beauty of this game is there's not many winning positions, you know, so actually you can sort of learn them and you could become an expert, and the children may want to do this, and this is actually quite good. Now, earlier on in the game, at the moment, red is not blocked, but if but red is one to move next, and wherever red moves to, blue can win if he plays correctly. So in 1 move for the 3 on the left-hand column, in 2 moves for the next 3, and 3 moves for the next 5 possibilities shown there, and in 4 moves for the last one. If blue is playing correctly and is looking several moves ahead, then blue can win in each of these games. Lenny is going to do some activities with string here about the converse of using the converse of Pythagoras' theorem.
In a very simplified format. You don't have to prove anything here, but with a right angle triangle, the squares on the smaller side are equal to the same area as the square on the longer side, a hypotenuse. So that's what Pythagoras is the theorem. And I'm going to use the converse of that to create a right angle triangle maker. And the way I'm going to do it is I'm going to get a piece of rope and I'm going to divide it into 12 equal sections, or 12 equal spaces. So if you notice here, I'm not sure if you can actually see this clearly, but there's a method that builders, plumbers use today, lots of contractors use to create a right angle, and it's called the 3-4-5 triangle. And this will always create a right angle, because the 3-sided square equals 9, the 4-sided square equals 16. If you add 16 to 9, that equals 25, and the square root of 25 is 5. That's how we end up with 3, 4, 5. That's a nice, easy number. 12 is a lovely number because it divides by 2, divides by 3, divides by 4, divides by 6, 1 in itself. So a lovely number, and that's why we came back. It's why the Babylonians effectively learned to count.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
It's actually why we've got 12 hours in the clock, and 60 seconds comes from the fact that they multiplied 5 by 12. That's why we've got 60 seconds, literally. All of that is immaterial to what I'm actually going to do. So I am going to create a 3, 4, 5 triangle, and I'm going to do it with some string or some cord. String works, which is thin. Cord works better. Rope may work, as long as it's not too thick, may work even better. So this is what we're going to create, a 3, 4, 5 triangle. And I'm going to show you how to divide the loop up into 12 equal lengths. So here we go. Yeah. And, try and adjust things so you can see what I'm doing. So this is a length, I call it cord rather than rope. And this one, I suggest having it between, ultimately it doesn't matter how small or big you do this. The smaller you get it, the more difficult it's going to be to divide it into 12. So this turns out to be roughly 3 meters. I know that because if I go once, twice, 3 times, that's roughly 3 meters. I know that. It's how Romans used to do it. So I'm going to tie the loose ends together. So I go right under left and twist anti-clockwise or counterclockwise. Sorry, right. So I'll do that again quickly. Right under left and twist counterclockwise, and then left under right, or the opposite. Yeah, left under right, and you twist clockwise. And if you pull them together, that knot should tighten. That knot should tighten. It should tighten on itself. If you're not absolutely confident, you can do another twist and another knot. It just makes
that's great.
Okay, so I'm not going to do that, and I'm hoping that's not going to slip. Okay, so there we have a loop, continuous loop. We want to divide this up into 12, but before we do that, we're going to divide it into 2, then we're going to divide it by 4, and then we're going to divide it by 6, effectively. Easiest way to do that is make sure our knot is up one end, okay, as high as you can make it, and grip it. Okay, and then all I need to do is pull the cord not too tightly until we get to the other end. What I sometimes do is I get 2 pens or 2 pencils, because your fingers can add a little bit of error. Make sure that the knot is sitting over 1 pen, pull it tightly, and now you know you've got 2 equal lengths. So you've got 2 equal lengths. We'll grip this end, and there's a couple of things we can do here. What I do was I got a short length of string, and I tied a little knot, tight little knot. I won't double knot it. So I'll just put that there. I have got one I prepared earlier, so we can do it this way, pull it tight, and make sure it's right at the end. So you've got 2 equal lengths. Divide this by 4 equal spaces. What I do is pull the loop out, give it a twist, so it's crossing in the middle, and then I have 2 loops, and 4 lengths, 1, 2, 3, 4. And I do the same thing. I get pencils or pens and put them in between the 2 loops, pull it tightly so all our lengths are the same, and make sure the 2 knots we have now are sitting over the end of the pen, and my spaces in between are equal lengths. So I can tie some new knots, or I might have a pen handy, and perhaps I could make a mark right at the end on each piece. If I can do this. Okay, right then, so I'll whiz on. Okay, to get our in-betweens, so if I had a clock, I've already created 12, I've created 3, I've created 6, I've created 9. I want to create 2, 4, 6, and 8. I'm going to divide this by 3. So I'm going to loop this 3 times, create 3 loops, cross and drop. So it's a small loop and a large loop. Cross again and bring that up. And now I have 3 loops. 3 loops, 2 pens, pull all the loops so they're equal lengths. Make sure my knot's over. Okay, and I've got a couple of methods. I'm going to do the quick method now. At these ends, 3 ends, I'm going to make a mark there and a mark at the end there. Okay, I could tie knots with string and go to the other ends. And I've got a knot with 2 spares there. Okay. So I've got 1, 2, 3, 4, 5, 6 marks, 7 marks I think I have now. So I've still got some missing. And there is a clever way that we can do that. So if we pull our loops out, now then, so we do have some spaces, but the easiest thing to do, grab our knot, pull it out. We know we've got one at that end. We've got one at that end. If I turn this around and move it, and come around, so what I'm doing is I'm moving the knots round. So I've got 1 space round from the knot. Where the spaces are will be filled in by marks or knots that you've already created. And then all you do is you copy those across. So where they meet, where there's 1 knot, you can add another knot. Sorry, if that's a bit clearer like that. Or you can match the 2 marks up. So you can fill in the gaps by what you've already got. And you can keep moving. So what we've effectively got now are 12 spaces, 12 knots. Okay, and we know that 3, 4, and 5, 3 plus 4 is 7, plus 5 8 to 12. So we've got our 12 marks. So there are a couple of methods now. So because I'm on my own, I'm going to use my pegs. And I'm going to start from the big knot. That's my knot. I want to count the 3. So this is going to be the right angle where that knot is. I want to count 1, 2, 3, and I'm going to put a peg over that knot. So that's 3 spaces away. I'm going to go to the other, back to knot. I'm going to count 4. 1, 2, 3, 4, and I'm going to put another peg down. Here we are. Here's our second peg. So I've got my 3 and my 4. Okay, and I'm going. What we're left with is the 5. Okay, and just for good measure, I'm going to put another peg over our main knot. So we have a 3, 4, 5 triangle. Okay, now what you could do, you could do away with the pegs, and you could just get children to hold hold it at the knot. So you can get somebody to hold the main knot. You can get somebody to hold the knot 3 away, and somebody to hold mark 4 away. This will work for me though. I call it. It's just actually it's a towel rack. Over here. Maybe sure nothing loose. So I've got a nice straight line. 1, 2, 3 marks, and I pull. So there we are. So this is 3, this is 4, and we're left with the 5 straight lines. So if these are all straight, we know we've got a square, which would be 9. 3, we know we've got a square, which would be 16. 16 plus 9 equals 25, and we've got a 5 side here. So we know we have a 3, 4, 5 triangle, meaning that corner there is your right angle. So we've got a right angle maker, and this is effectively what builders do sometimes. If they haven't got anything else, they'll cut up a bit of wood and they'll create a 3, 4, 5 triangle. You can do this with equal, a very large rope. You can go out on a playground, and you can do the same thing with a very long length of rope. So you can make it as large as you want out on a playground, this size inside a room, or you could even make it smaller. So it's a bit of fun.
Thank you, Lenny. That's fantastic. What you've actually done is to show how you can be sure that's the right angle, and it's a good revision lesson for children. If they already know Pythagoras' theorem, what it does help them to sort out is the difference between the idea of a statement or theorem and its converse. Okay, so now, thank you, Benny. That was great.
Thank you.
Now, here's a summary of what we have been doing in this workshop. So you can see some of Lenny's flower of life patterns there, and you can see this activity with his 3, 4, 5 triangle. You can also see the cryptorhythm, the football challenge, the matches, and the football. So, Caroline, of all these things, and anything you want to comment on?
I really like the puzzle aspect of the L games. I found playing the game, I got a little bit frustrated because nobody was winning, but the puzzle aspect, what positions would you put the dots in if you know, if this was your situation? Is it possible to win with this situation? I found that aspect really intriguing with it and engaging.
Lenny, what do you want to comment about just one of the activities?
I think I maybe focusing on what I was doing. You can just create with bits of plastic and bits of card. You can create some beautiful shapes, and maybe we'll set this out as a challenge and see how clever your children can be, how creative they can be. See what shapes, and then you can keep getting larger and adding to it and adding new circles. So just have fun.
Okay.
Pam commented on Lenny's presentation using the finger phalanges, I didn't know that word, to demonstrate the factors of 12, and Talu really liked the presentation you just gave with the
Thank you very much. It's very kind of you.
Okay, so there's so much statistics in football, so many facts, and it's so many questions you can ask, so many ways that you can represent the data, and people are interested in football statistics. So you might be able to invent with your class, you may actually ask them to help. Well, what investigations, what can we try and find out and draw in represent the data? What can we try and find out about football and share these what we found in charts and summaries? So on the Aiming High website, there are lots of worksheets. There's inclusion and home learning guides with activities for learners of all ages. And here are some links. There are some links to related ideas and lessons. In a soccer stadium, we haven't discussed this afternoon, but it's a very nice example about a soccer stadium and you can solve it either by scale drawing. So for older primary or lower secondary learners, they can do this problem. So if you like to look that one up, or they can do it using the oldest learners can do it doing trigonometry.
Tony, just to say, Melanie said with the L game, you could have teams and only one person on each team is allowed to move. So the others have to describe the movement and give them instructions on how to move.
Great idea, Melanie. And you can do that as a whole class activity where half the class is one team and half the class is another team. It's a great idea.
Every day, Tony posts a daily maths starter on the Facebook page.
It's time to say goodbye.
Thank you very much, everybody.
This is a Global Teacher Empowerment Network video collaborating with AIMSEC and the Aiming High website. Our mission is to benefit children in disadvantaged communities all over the world by empowering the teachers who teach them mathematics.